Good afternoon. In today's lecture, we will be starting a new topic. Today's lecture, we will be covering the waves, definitions of some quantities, and then the traveling wave equation. And we will see how does a wave propagate in a medium. So our lecture today from chapter 13, covering text sections 13.1, 13.3, and 13.5. In next lecture, we will be studying the interference due to the reflection of the traveling wave and the constructed standing waves. All waves are caused by oscillations. We have several examples in the nature, including the light wave, which is basically due to the oscillations of the variation, the electric field and the magnetic field that causes the propagation of the light. We also have the sound waves being generated due to the oscillations of the air particles. For example, if you put your hand in front of your mouth, you can sense the vibration that your mouth, when you're speaking, is causing to your hand. So those oscillations are causing the sound signal to be propagated in the space. A simple example of the waves can be throwing a rock in a pond. The rock will cause the water level to go down. And then once this water is released, it will start oscillating up and down till it dissipates. But this oscillation in the water surface in the pond will create those ripples that you can see propagating in all directions on the surface of the water. So those are also waves. So those waves create, or they are happened by those periodic functions that are repeating themselves at regular intervals. And one example of those periodic functions is the simple harmonic motion, which is basically caused by the stored energy due to the displacement. So it is proportional to the displacement, and you can see that in the mass spring experiment. So the driving force is proportional to the displacement away from the equilibrium position. We're going to look at the simple harmonic motion more later on, but before we do so, I would like to introduce first the period and the frequency of a signal, of a periodic signal. So what is the period? The period defines the time that wave takes to complete one full cycle. That's called the period. The unit for the period is seconds. The frequency, on the other hand, is the inverse of the period, which basically defines the number of cycles you do per second. The unit for the frequency is hertz. So the relationship between the frequency and the period is the frequency is the inverse of the period. Now let's look at the simple harmonic motion in this example to understand how does it happen. This periodic signal that can be simplified in its simplest way with a sinusoidal function that relies only on one single frequency is happening by connecting this spring to that mass And if we assume that it's an ideal system, which means it's frictionless, then by pressing this mass or pulling that mass to the right or pressing it to the left, you are storing energy in the spring. And then once you release it, this energy is released, causing the mass to accelerate till it reaches the equilibrium point where the force becomes 0, and then start to decelerate again till it reaches the second point. So if we look at this mass as the equilibrium being the 0 reference for the x-axis, then I have an amplitude to the right that is positive and amplitude to the left that is negative, where the velocity or the speed right at those 2 points equals to 0, because that's the point where the mass comes to a stop and then flipping the motion. So pressing it this way will result into pushing this mass this way, continuing all the way till it reaches that point and then flipping back again. So if the system is ideal and I have 0 friction, then this system is going to oscillate to infinity, indefinitely. It's not going to stop oscillating. So to represent this motion, we represent that motion with a single frequency with a sinusoidal signal. So the sinusoidal signal is an ideal periodic function that we can use to represent such a motion. Again, as I said earlier, the period is defined by the time it takes to finish one full cycle, which means from the beginning till the end. I can look at the beginning and the end of this sinusoidal function from here to here. This time is the period. Or I can take this time between those 2 peaks, or I can take the time between those 2 peaks, as long as I'm covering one full cycle. So this function, the one that you're seeing right now, assuming that this is my displacement, and that's my x-axis here, that is a function of time, then this function is a minus sign function, which is an inverted sign, because as you can see, I'm going from 0 to minus a, which basically means it's a sine function multiplied by minus 1. So a sine omega t times minus. So that's an inverted sign. Now the angular frequency, this angular frequency is 2 pi f, given by this expression, where the unit for the angular frequency is radians per second. Now, this motion is an oscillation, as you can see, represented by a sinusoidal function. If we have a mass that is attached to a spring and pulled 20 centimeters to the right, pulling it 20 centimeters to the right, it's very important to understand what is the function here. If I pull it to the right 20 centimeters and I released it from the right side, what function do I have? Is it a sine? Is it a cosine? Is it an inverted sine or an inverted cosine? It's a cosine, because I'm starting from the maximum at 0. Right? Thank you. So if you start at the maximum from 0, then you have a cosine. If you start from the minus a at 0, then you have an inverted cosine. Okay, so now comes to the question here. What are the amplitude and period of the resulting cosine function? Now we know why it is a cosine that describes the position of the mass as a function of time. It's pulled to the right 20 centimeter, which means that the amplitude is 0.2 meter, right? So the amplitude is 0.2 meter. It completes 20 oscillations per in 10 seconds. What does this mean? This means that the frequency is 20 divided by 10. Which is 2 hertz, or the period is 1/2, which is 0.5 seconds. So the answer to this is C. Any questions so far? So what is the wave? The wave is a disturbance that is happening to my medium. This disturbance is causing that medium to start oscillating, and then this oscillation will start propagating in all directions. This disturbance will cause an energy to be translated to that medium and then propagating in that medium. Keep in mind that the matter itself does not move forward. It's only oscillations, only disturbances in terms of oscillations that's happening in the medium that causes this signal to propagate. Think of the rock that you threw in the pond. The water where the rock hit the surface of the water did not move. However, it did oscillate, and this oscillation was translated into ripples that were propagating in all directions. Those waves are described by those quantities that we have started introducing: period, frequency, and as we will see later on, wavelength, wave number, wave velocity. Those waves, as we will see in the next lecture, those traveling waves can reflect. When they see an obstacle, they could reflect. They can reflect. Now, the reflecting back will cause an interference with the traveling wave that got reflected, and this will cause some regions to be constructed and destructed using the superposition theory, if you want to think about it, and then creating what we call the standing waves. We will see that in the next lecture. But today, we're focusing on the traveling waves. Those waves that can travel in the medium. Again, the standing wave will be due to the reflection of those traveling waves and interfering with the traveling waves. We'll see that in more details in the next lecture. So now let's classify those waves into mechanical and electromagnetic waves based on the medium that those waves are being generated in. For example, the pond example, that's a mechanical wave. The sound is a mechanical wave. However, the radio frequency and the light waves, those are electromagnetic waves that are happening due to the oscillation in the electrical signal. The oscillation here in the current causes this oscillation to generate electromagnetic waves through generating a time-varying magnetic waves, and then this time-varying magnetic waves generates time-varying electrical wave, and so on and so forth. And this is how the signal is being generated and transmitted, the radio signal. You can look at the FM or those AM signals as an example of those carriers that are oscillating and transmitted through the air. So you have your mobile phones, your radios, your radars, all those instruments, they use the waves, the radio waves to transmit and receive signals. We can also classify those waves based on the orientation of oscillation. We have agreed upon that this oscillation is causing the generation of those waves. We have two types of oscillations. Matters still do not move forward, but there are two types of oscillation. Either the oscillation is perpendicular on the direction of the motion, and the example for this is the pond, the one that you threw the rock in, or the oscillation is happening along the direction of propagation, and this is the sound waves. In the sound waves, the vibration or the oscillation is happening along the direction of the propagation, and that's what we call the longitudinal wave. The transverse wave, on the other hand, the oscillation is happening perpendicular to the direction of the propagation. So let's watch this video to see the difference between the longitudinal wave and the transverse wave.
In a longitudinal wave, there is a disturbance that makes
Okay, I'll talk.
Along the direction and
So the longitudinal wave, as you can see, the oscillation is happening along the direction of the propagation. By applying the oscillation along the direction of the propagation. The transverse wave, on the other hand, by applying the oscillation such that this oscillation is perpendicular on the direction of the propagation. This is what happened in the pond. However, the longitudinal wave is the sound wave. So any wave can be described, as I said, if we're using one single frequency in a one single sinusoidal function in its simplest way, ideally assuming one single frequency. So in this case, I can represent the displacement that's happening in the medium by the variable y, where a is the amplitude and the sine is the function that represents the periodic function. However, theta in this case, as we will see more in details later on, is a function of space and time. Why? Because that wave, in order for that wave to propagate, it should be a function of the space and also a function of time. So how is this happening? It is happening and represented by this function. So this function is a function of a space x and a time t. This is the wave function. This function represents a wave that is propagating in the positive direction and also propagating in the negative direction. So we have here the plus minus. So keep in mind that if a wave is traveling in the positive direction, then the sign should be negative. If the wave is traveling in the negative direction, then this sign should be positive. A is the amplitude, T is the period, and lambda is the wavelength. what does a wavelength mean here? The wavelength, as we have seen, the period is the time the time that one cycle takes to complete. The wavelength in the space domain is the length of one complete cycle. So in the space domain, the wavelength is the length of one complete cycle, and the period in time domain is the time it takes one cycle to complete. So the wavelength has a unit of meter. Okay, so keep in mind the minus represents a wave propagating in the positive direction. The plus represents a wave propagating in the negative direction. So you can see here that we have the 2 pi outside those two parentheses. Now, if I am to multiply this 2 pi, distribute this 2 pi, then I would have 2 pi over t. This 2 pi over t is the angular frequency. And the 2 pi over lambda is the wave number that we will talk about in next. So what I just did here is distributed this 2 pi over t and x over lambda. So here I have now the wave number that is 2 pi over lambda, and I have this angular frequency as 2 pi over t. This is the function that represents the wave. Again, plus negative direction, propagation. X here represents the direction of the propagation and the x-axis. So what we have here is the wave number. And what's this wave number? Is the angular frequency change per unit length, which is 2 pi over lambda. Okay, so now we'll take this function as our wave function. We understood that this minus sign means that the wave is propagating in the positive direction. This x variable here defines the axis that I am propagating on in that direction. So right now, the displacement or the oscillation is happening along the y-axis. The propagation is happening based on this sign, however, along the x-axis. So let's see how we can derive or plot the propagated wave. So the first thing I will do is I will put the function that we have agreed upon to be my wave function, and I will pick a sign of minus, the negative sign, in order to get a propagation in the positive direction of the x. So my function is y equals to a sine omega t minus k x. That's this is my function that I would like to plot. I will put my coordinates here. Y, x. Since I'm plotting against the x-axis, which is basically I'm in the space domain, I will write those distinguished points for my wave in terms of my wavelength. So the first one here, x0, the next point is lambda over 4 at a quarter of a lambda, then lambda over 2, 3 lambda over 4, lambda. This is the length of one full cycle. So what I'm going to do now, I will plot that wave, and I will show you how this wave is moving with time. But to do so, I'll take it step by step. What do I mean by this is, I will freeze the time and plot in space. And then I will plot in space for the next moment in time. So I will take them one time at a time. I will start with t equals 0. The points that I will take are t equals 0, t equals t over 8, and t equals t over 4. I will divide them, I will discretize them into time snap times. Those times, I will freeze them, I'll take them at snapshots. So here, I'll start with t equals 0, and I will rewrite now the function for t equals 0. So if I am to rewrite this function for t equals 0, my function, so here at t equals 0, I have y equals to a sine omega times 0 minus k. Now k, I will write it in terms of lambda. So k is 2 pi over lambda times x. So now my function for t equals 0 becomes the following: a sine minus 2 pi over lambda times x. This is the function that I want to plot in the space domain. This represents the wave at t equals 0. So in order to plot this, I will solve it for all those points. For x equals 0, I have y equals to a sine 0, which is 0. So my first point is this one, 0. At time equals 0, I have 0 displacement. Next one, x equals to lambda over 4. Y is a sine minus 2 pi over lambda times lambda over 4. Lambda will cancel, 2 as well. So this one is a sine minus pi over 2 or minus a. Right? So the next point, when it's lambda over 4, it is minus a. I want to put those amplitude. So this is a, this is minus a. So for lambda over 4, the point is here. For x equals to lambda over 2, a sine minus 2 pi over lambda times lambda over 2. Lambda cancel, 2 a sine minus pi, which is 0. So the third point is here. Now, I know if I continue solving for 3 lambda over 4, I would be getting the point to be at A. And I also know if I do it for lambda, I would be getting the point to be 0. If I continue even for 5 lambda over 4, I would be getting the point to be minus A. Now, if I am to draw this function, then this function is going to look like this. So this is for t equals 0. This is the wave function for t equals 0. Now, if I want to calculate or plot the wave for t equals t over 4. I'll start with t over 4, not t over 8. And I'll show you why. Then at t equals to t over 4, I need to rewrite the function again. I should start from y equals to a sine. Now here omega is 2 pi over t. The angular frequency in time, in the period, in terms as a function of the period, is 2 pi over t minus 2 pi over lambda times x. Now I will substitute. Then this is a sine 2 pi over t times t over 4 minus 2 pi over lambda x. And the function now becomes a sine. T is going to cancel. Pi over 2 minus 2 pi over lambda x. Now this is the function that I need to plot. When it was t equals 0, that was the function I wanted to plot. So let's plot this function for the same points. X equals to 0. Y is x equals to 0, then y is sine pi over 2. And this is a. If x equals to lambda over 4, then y is a sine pi over 2 minus 2 pi over lambda times lambda over 4. This equals to a sine pi over 2 minus pi over 2 equals to 0. Then the next point. So the first point was a at x equals 0. At x equals lambda over 4, it was 0. Now, if I continue solving for the remaining points, at lambda over 2, it would be minus a. At 3 lambda over 4, it will be 0. At lambda, it will be a. At 5 lambda over 4, it will be 0. It's a periodic function. Think about it. So if I'm now to plot this, so this one is t over 4. Now, why I did not do t over 8, I will do it now because I can now do it easily this way. I'll show you how. It will be here. It will be here. It will be here. It will be here, here, and here. So now if I'm to plot the t over 8, so this one is, the red one is t equals t over 8. Now I want you to pay attention to the peak of the signal here, of the wave here. 1, 2, 3. Now we plotted the wave at the 3 moments, t equals 0, t equals t over 8, and the next one t equals t over 4. Notice that at t equals 0, this peak was at 1. At t equals t over 8, this peak moved to 2. At t equals to t over 4, that peak moved from 2 to 3. So the wave is moving. The whole wave is moving. Now, if you look at one position, let me draw this line here. At one position on the x-axis in space, one position in space, what can you notice here? You can notice that at t equals 0, this position was at this location. At t equals to t over 4, t over 8, it went down to here. At t equals to t over 4, it went down to here. And then it will continue till it reaches the minimum, and then we'll start moving up till it reaches the maximum. In other words, that moment, this position in space, this position in space would be oscillating up and down. And this oscillation is the cause for the wave to propagate. So matter-wise, this position in space is oscillating up and down, and this oscillation is causing this wave to propagate, this energy to propagate. But the medium, this position of a space for that medium is not moving. It is oscillating up and down. Is that clear? This is the wave propagation, or this is the traveling wave due to an oscillation. Okay. So moving a distance that is lambda, because lambda at the end is a distance. Moving a distance of lambda, which is the full length of one complete cycle, during a period of t, basically defines a velocity. Distance and a time defines a velocity, and that would be the velocity of the wave. So the velocity, the wave velocity is lambda, the time this wave traveled for one full cycle, divided by the period of the one full cycle to happen in. So v, the speed, is, or the wave velocity is lambda divided by t. Now, if you substitute t with 1 over f, this is a second expression that you can calculate the wave velocity in terms of the frequency and the wavelength. So keep in mind, in order to describe a wave, you need to find those quantities: wave number, angular frequency, period, frequency, and also the wave velocity. Now, the question here is asking us is the following. If I know the wave number and the angular frequency, can I determine the speed of the wave? In order to determine the speed of the wave, you need the wavelength and you need the period, right? Or the frequency. Now, the wave number does have the lambda, does have the wavelength. And the angular frequency does have the period, right? Which is the time. So if I divide the angular frequency by the wave number, I can get the wave velocity. So yes, indeed, I can calculate the wave velocity by dividing the angular frequency by the wave number. So let's do this example. In this example, we have a wave that moves along a string in the positive x. So it's extremely important to know what direction the propagation is happening through and what polarity. Is it negative, is it positive or negative? So here we have it going in the positive x direction with a speed of 8 meters per second and a frequency of 4 hertz and an amplitude of 0.05 meter. What are the wavelength, wave number, period, the angular frequency, and at the end we need to put all this in the wave function to describe that wave. So let's do so. So what we have here is the following. We have the angular, we have the amplitude 0.05 meter. We have the speed 8 meters per second. We have the frequency 4 hertz. I need to calculate the wavelength lambda. So we have the wave velocity, which basically v equals to lambda f. So lambda is v over f. Lambda is 8 divided by 4. Lambda equals to 2 meters. What about the wave number k? Wave number k. So you can see that this example is straightforward implementation here. So the wave number k is 2 pi over lambda. And this is 2 pi over 2. And k is pi per meter. C, the period is 1 over f, 1 over 4.25 seconds. D, the angular frequency, omega, is 2 pi f, or 2 pi, f is 4, which is 8 pi radians per second. Then we need to put all those quantities in the wave function such that the y represents the displacement and the positive x represents the direction of propagation. So in this case, we have y equals to a sine omega t, positive direction minus kx. So this is 0.05 sine omega is 8 pi t minus the wave number is pi x. So this is the function that describes this wave. Any question about how did we calculate this wave function? If you have no question, then we will end our lecture here, and I will see you on Wednesday.